Hi, let's make a traffic light using a finite state machine. Okay. The finite state machine is an abstraction, and so we're going to begin our design by looking at the input-output. Okay. So we have two roads. Cars are either going east or they're going north. Okay. And so our first outputs are the ability to control the two traffic lights. So we're going to connect up 3 bits to the light that's gone east, and we're going to connect 3 bits for the light that's going north. Okay, so what we have is a 6-bit output. We have 2 car sensors. The car sensors will tell us whether or not cars are coming. And so the north sensor here is going to be connected to PE1, and the east sensor is going to be connected to PE0. So we have 2 bits of input. And so to understand how this works, we can see that the input for this machine is got 4 possibilities. If both sensors are low, that means there's no cars. If both sensors are high, that means there are cars both directions. Both roads have cars. And we saw, since we tied PE1 to the north sensor, this means there's cars just on the north. And PE0 is tied to the east sensor, and so this means we have cars just on the east. Okay. So once we get a good understanding of what our input-output is, the next is to capture the essence of state. Let's begin the design by thinking about the states. Okay? A state represents what the machine is doing. What do we believe to be true? And so what I'm going to do is list the possibilities that can be happening. So cars going north through the intersection represents a state. We're going to allow cars to go through north. Later on, I skipped a spot, we're going to allow cars going east. And in order to flip between these 2 states, we're going to have to stop or slow down the north cars. And similarly, after we're allowing the cars to go east, then we're going to want to stop or slow down the east cars. And you notice I don't have a state where cars can go both north and east at the same time. I don't have a state where no cars can go, because it's a very simple thing. So once I've figured out what my states are, the next step is to do a mapping from the states to the output. And remember that PB 5, 4, and 3 were the lights for the red, yellow, green, the lights for the east road. So if I want cars to go east, I'm going to have to turn on the green 0, 0, 1, and the other 3 bits, the PB 2, 1, and 0, which is also red, yellow, green, I'm going to want that to be red. So 1, 0, 0. So that will be the output pattern, allowing cars to go green. Similarly, if I want cars to go north, I'm going to want to turn on this light and that light. 1, 0, 0, 0, 0, 1. When I want the cars to go slow down on the north road, I'm going to flip this green light to a yellow light, okay, and leave the red light on the east. And similarly, when I want the east cars to slow down, I'm going to turn on the yellow light for the east, 1, 0, 0, 1, 0, 0. So in a Moore machine, we see a one-to-one mapping between the state that we're in and the output pattern. All right. So once I've got a sense of my states, the next step is to figure out what to do with the inputs. All right. Next, we got to figure out what to do with our inputs. In a finite state machine, the inputs cause the machine to change states. So let's write down our states again. Okay? I'll use this shorthand GoN for meaning going north. And remember, we had the output pattern of 1, 0, 0, 0, 0, 1 to allow the cars to be green in the north direction and red in the east direction. And then I had a wait north state where the north state went to yellow and the east state remained red. Then I had a go east state where the light on the east road was green and the light on the north road was red. And then I had a wait on the east road where there was a yellow light on the east road. So this is what we had from before. And so what I want to do now is think about what I'm going to do if the input were a 0, 0. And remember, what does that mean? That means there are no cars. Okay, that's what that means. So what I'm going to think about is if I'm in the go end state, if I'm in the go end state and the input is 0, 0, that means there are no cars. I'll just leave it right there. It's fine. I'll just leave it. Similarly, what does it mean if the input is a 0, 1? You remember that the 0th bit was connected up to the east road. That means there are cars that are just on the east road. Okay? And if there are cars on the east road and the light is on the north road, what I'm going to want to do is to stop the light, but I can't go directly. I have to first turn it yellow. Okay? And so let's finish the progression here. So if there's a car on the east road, I'm going to make it go wait, and then I'm going to make it go east. And then I'm going to stay right here on the east road. See that? And so we can see here what we've built so far is if we start out in a state and there's a car on the east road, it'll go to wait, and then it will go, it'll flip into this state and then go into that state and stay there. So the light will go east green if there are just cars on the east road. That's what we're doing. Okay. What about the 1, 0 state? Okay. Remember, the 1, 0 state is cars just on the north road. If I'm already in the north road and there are cars on the north, I'll just stay there. See what I'm doing? I'm using my intuition to say, what if I'm in these states, what if the input were to stay? Probably the most interesting one, and the one that's most illustrative of what's going on, is the 1, 1 condition. And this sort of captures the entire finite state machine in its entirety. So let's do that one next. And this is if there are both cars. And if you think about what you want to have happen, if cars are on both roads a busy day, what we're going to have it do is basically cycle through. Okay? And so if the light is green and there's both, it'll go wait, and after wait it will then go east. And then after go east it'll go wait east. And then after wait east it will go back to go north again. And so for this particular input case of 1, 1, we will see it cycle through here, allowing cars to go east, and then allowing cars to go north and repeating back again. All right, so let's do. We got to fill in this thing because we got to. What if everything happens? This state here is kind of interesting because regardless of once the light is yellow, regardless of the input, I'm going to go east because I don't want the light to go green on the north, yellow on the north, and then back to green on the north. That's a silly thing. So I'll just go all the way to green on the east once I go yellow on the north. Similarly down here, regardless of the input, I'm going to go back to north after the east light goes yellow. Let's do an easy one. If the lights is green in the east road and there are no cars, I'm just going to stay right there. That's a fairly easy one. But let's do a hard one. Let's say the light is green on the east and there's just cars on the north. That's this condition here. No reason to stay green on the east. I want to flip over to north, but I can't get there directly, so I have to go through this wait state. Okay? So now let's sort of imagine the sequence of steps that occur if I'm in the east green and the lights go and the cars are just north. It will then go into this state. It will then go into this state and then come back to that state here. Okay? So we see that if I just have north, it will go through the east yellow and then flip up to green on north. All right, so we've built this state transition graph. And now we're going to map this state transition graph into the data structure, which will be our finite state machine. Let me show you that this state transition graph is exactly the same as the finite state machine graph here. So in a finite state machine graph, we have the name of the state, the output pattern 1 0 0 0 0 1, wait n, right here 1 0 0 0 1 0. You see that's this. We have go east, which is 0 0 1 1 0 0. That's this. And we have one more, wait east, which is 0 1 0 1 0 0. Okay. All right. So what I'm going to do is do this mapping from the graph to the table. Okay. So this term here, okay, represents this arrow 0 0. Okay. I'll go along here. That one represents this arrow. This one represents that arrow. This one represents that arrow. Okay. Now these are all easy. They all go that way. 1 2 3 4. 0 0 0 1 1 0 1 1. And then here, this one, this picture right here is I'm going to stay in that state 0 0. I'm going to stay in that state on a 0 1. I'm going to go over here on a 1 0, and I'm also going to go over there on a 1 1. And then these all go back over there. Zero zero 0 1 1 0 1 1. Okay. So you see that the exact same information in the table is in the graph. Okay, so I'm going to work with the table because it'll show a simpler map to the actual code. So I'm going to erase the table and then show you the code. Now here's the beauty of the finite state machine design, and that is that there is an abstraction here in this table or in that graph. But when we do the translation into the code, we capture absolutely everything about that machine. And so what we're going to do is we're going to see that when we write the code, the finite state machine, which is S-type, the finite state machine, okay, we're going to capture everything. Okay, there are exactly 4 states, so we're going to have 4 states in our table. I did leave off the time, so I'm going to go ahead and paste that in so you'll see it. I'm going to stay here for 30 seconds, which will mean 1,000. I'm going to stay here for 5 seconds, 30 seconds, and 5 seconds. And this is the time in 0.01 seconds, or 10 millisecond. All right. So for each of the states, we're going to capture the output. So that number right there, this one number right here, is 0x21. Okay. And then I'm going to capture the time, which is 3,000. That's that number. And now these are the next states. So I'm going to capture those exactly the same. Go in. That's this one. Wait in. That's that one. Go in. Wait in. This is all the syntax I got to do to make this look pretty. That's my state. So you see that this line of C code and that line of that table are mathematically equivalent, 1-to-1. That's how I write the other states as well. This 22 is right there. There's the 500, and then I'm going to capture the 4 states here, which are all go east. And there's my 0C, 3,000. Again, that number right there, 0C. And there are my 4 states. Go E, wait E, wait E. And then we got one more, which was the 0x14. That's this number. 5 seconds. And then all of these are go-ins. All right, so what you've seen here is that there is a 1-to-1 mapping. That means no more, no less information. 1, 2, 3, 3 semicolons, 3 braces and a semicolon. A 1-to-1. That means that there's no more, no less information. So we've captured in C code all the information that we had in our table. All right, the next step is the engine. We'll write the finite state machine engine. This is the part that's repeated over and over again. We'll have a index which will represent our state, and that will we've got to begin somewhere, so we'll begin with the north state. This is a more machine. In the more machines, we're going to do our output. We're going to send out to our port, right? That's going to be port B. We're going to send our output out to equal the finite state machine. The output is a function of the state, and we're going to capture the output parameter. So that number is going to be one of those 4 numbers. It's going to be, if s is equal to 0, this number here is going to be a 0x21. If s is equal to 1, it's going to be a 22, and if s is equal to 2, it's going to be a 0c, and if s is equal to 3, it's going to be a 1,4. Those are the 4 possible outputs. That's going to happen right there. Okay. The next thing I'm going to do is wait, okay, and I'm going to call my wait 10 millisecond routine, and I'm going to pass in the parameter for that state. So again, some of the states are going to wait 30 seconds, and some of the states are going to wait 5 seconds. And the wait time is a function of the state that I'm in. Now I got to do my input, so I will read my input from port E, okay, and I want the bottom 2 bits, 0x03, and so now you know I have a number which is 00011011 from the bottom 2 bits. And now here's the fun part. We're going to change states. We're going to go to a new state, and that new state is a function of the old state, and it's a function of the input. So we had 4 next states, and so I'm going to index into that list, which again is a function of the state that I'm in and a function of it. Now that's a finite state machine. We're just going to do that over and over again. Now you'll see the details in the code. Now you try it.